The sky above us is never the same. Sometimes soft and calm, other times heavy and full of power. Clouds accompany us every day, shaping the mood of the light, the temperature, and even the climate, while hiding secrets that have fascinated humankind for centuries. They've witnessed history, inspired art and poetry, and even though we see them daily, they remain mysterious and full of wonder. In this episode, we'll look closer at their extraordinary life and the impact they have on the world around us. Clouds are not just soft white shapes. Floating overhead, they are complex atmospheric systems in which every element plays a role. Each one is made up of billions of microscopic droplets of water or ice crystals suspended in the air. These tiny particles form when moisture in the atmosphere condenses or freezes around dust, sea salt, or pollution, what scientists call condensation nuclei. Without them, water would remain as invisible vapor, never becoming the visible textured masses we recognize as clouds. Clouds form at different altitudes and under different conditions. High clouds, such as cirrus, form above 20,000 feet and are made mostly of ice crystals. Their thin, feathery shapes often foretell a change in the weather. Mid-level clouds, between 6,000 and 20,000 feet, can be a mix of water and ice, often creating layered formations that sometimes bring light rain or snow. Low clouds, below 6,000 feet, are dense and moisture-rich, filled with water droplets. These include cumulus, stratus, and nimbostratus clouds, which give us fog and heavy rain. The incredible variety of cloud shapes and colors comes from differences in temperature, humidity, wind, and air turbulence. Clouds billow, swirl, stretch into long bands, or rise like towers, all expressions of the atmosphere's restless dynamics. Their color depends not only on how much water they hold, but also on how sunlight hits them. White clouds reflect most of the sunlight, while dark gray or nearly black clouds are thick, water-laden, and ready to release rain. What's even more fascinating is that clouds often contain microscopic particles of pollen, bacteria, or sea salt, some of which can trigger rainfall, influence atmospheric electricity, or even affect climate patterns on both local and global scales. In a way, every cloud is a tiny laboratory of chemistry and physics, where air, water, and solid particles interact in hundreds of ways, constantly shifting and evolving. Beyond their beauty, clouds play a fundamental role in regulating Earth's climate and sustaining life. They help control temperature, reflect a portion of solar radiation, trap heat at night, and store water that returns to the surface as rain or snow. Each cloud is not just an aesthetic spectacle, but a living, dynamic system, one that meteorologists study to predict weather, climatologists to understand long-term patterns, and scientists to uncover the secrets of the air above us. Rain forms through processes called condensation and coalescence that happen inside clouds. A cloud is a collection of billions of microscopic droplets or ice crystals that are too small and light to fall on their own. For droplets to become heavy enough to fall, they must merge. Smaller droplets collide with larger ones, gradually growing until they reach a mass that overcomes air resistance and fall as rain. In high or very cold clouds, some of the water freezes first, forming ice crystals. As they fall through warmer layers of air, they melt and turn into raindrops. This process depends largely on temperature, humidity, and the movement of air inside the cloud. Strong updrafts, typical of thunderclouds, can hold raindrops aloft, allowing them to grow larger before finally falling as heavy rain or even hail. The color and intensity of rain also depend on the type of cloud and the size of the droplets. Light drizzles fall from low, thick, uniform clouds with small droplets. Torrential downpours, on the other hand, come from towering cumulonimbus clouds, where powerful convection currents rapidly grow and merge droplets into large, heavy masses of water. Rain, then, isn't just a simple result of condensation. It's the outcome of a complex dance between air currents, droplet collisions, ice formation, and condensation nuclei. Every rainfall is a unique process, shaped by hundreds of thousands of microscopic interactions that decide when and how water will return to Earth. Snow and hail form when clouds rise into colder, higher parts of the atmosphere. In these icy regions, water vapor freezes directly into ice crystals, which can merge into snowflakes that drift downward. Or, if the air below is warm enough, melt into rain before reaching the ground. The weather phenomena we see in clouds can be breathtaking and powerful, sometimes reshaping entire landscapes. Hurricanes, tornadoes, and thunderstorms are not just dramatic displays of nature's energy, but intricate systems of physics and meteorology, where heat, moisture, and air movement combine into raw, destructive force. Hurricanes are born over warm ocean waters, where surface temperatures exceed about 80 degrees Celsius. Warm, moist air rises and condenses into clouds, releasing enormous amounts of energy that drive the system. Winds spiral inward, reaching speeds of hundreds of miles per hour, forming the storm's iconic eye, a calm center surrounded by towering walls of thunderclouds. Tornadoes, by contrast, form when sharp differences in temperature and wind direction occur in the lower atmosphere, often within massive cumulonimbus clouds. Air begins to rotate, forming a spinning funnel that extends toward the ground. Though tornadoes last far shorter than hurricanes, their concentrated wind speeds can be even greater, producing devastating effects on everything in their narrow path. And then there are lightning bolts, electrical discharges that occur when charges separate within thunderclouds. Colliding particles of ice and water generate positive and negative charges that, when strong enough, create a dramatic flash. Lightning is not only a visual and acoustic marvel, but also plays a role in cleansing the atmosphere and triggering chemical reactions, including the formation of ozone. Extreme weather reminds us that clouds are far more than a picturesque backdrop. They are living, breathing systems of physics and energy. They store power, move water and air across the planet, and at their most intense, unleash the raw and awe-inspiring force of nature. Not all rain is the same. Some of it carries substances that can harm the environment. Acid rain forms when compounds of sulfur and nitrogen, mostly from industrial pollution and fossil fuel combustion, mix with water in the atmosphere, creating sulfuric and nitric acids. When these fall to Earth, they damage soil, acidify rivers and lakes, and harm vegetation. In the US and Central Europe, acid rain was a major issue in the 1970s and 1980s, when air pollution caused widespread forest die-offs in mountainous regions. Other rain is more unusual, like dust rains that carry fine particles of sand from the Sahara or other deserts across thousands of miles. These events can enrich ocean ecosystems with nutrients but also worsen air quality and affect human health. Some rainfall even carries microorganisms, bacteria, fungi, or viruses, lifted into the atmosphere and brought back down with the water. Sometimes they help plants grow. Other times, they can spread disease or alter local ecosystems. And then, there are micrometeor showers, tiny cosmic particles that drift through our atmosphere and settle invisibly within clouds, creating faint, almost undetectable showers of extraterrestrial dust. Though they don't affect life on Earth in any significant way, they remind us just how vast and interconnected the story of the sky really is. Finally, the most extreme forms of rainfall, like tropical downpours or monsoons, can unleash hundreds of liters of water per square meter within just a few hours. These events don't simply deliver life-giving water to rivers and soil. They often bring floods, landslides, and dramatic changes to local ecosystems. They remind us that rain is not just a symbol of renewal. It's a raw force of nature that humanity must respect. Clouds are among the most important regulators of life on Earth, even though at first glance they seem like nothing more than a beautiful decoration in the sky. Their role in the planet's climate system is fundamental. They reflect part of the sun's radiation, shielding the surface from overheating, while also trapping some of the Earth's warmth at night, balancing the planet's energy. Thanks to clouds, temperatures on Earth remain within the range that allows life to exist. Without them, nights would be far colder, days unbearably hot, and the conditions for plants, animals, and humans drastically different. Both land and water ecosystems depend heavily on clouds. Rain from clouds replenishes rivers, lakes, groundwater, and soil, shaping the regions where people and wildlife can survive. In tropical rainforests, every cloud is a wellspring of humidity that sustains dense, layered ecosystems where plants thrive and animals find refuge. In dry or semi-desert regions, even rare rainfalls can determine whether entire populations of plants and animals live or die. Clouds act as guides in the water cycle. Their presence or absence directly determines biological balance and the survival of species. The influence of clouds on humans is just as direct and complex. Beyond regulating temperature and providing fresh water, they shape weather patterns that affect agriculture, water supplies, and infrastructure. Some cloud formations, thunderstorms, tornadoes, or torrential rains, pose serious risks, yet they also provide scientists with valuable data about the atmosphere's dynamics and climate change. At the same time, clouds serve as natural filters. Rain and snow wash dust, pollutants, and microorganisms out of the air, helping cleanse the atmosphere. An intriguing fact is that clouds play a part in the global greenhouse gas cycle. Through evaporation and precipitation, they regulate the movement of carbon dioxide and methane between oceans, the land, and the atmosphere. Marine plankton, floating in the oceans, interacts with atmospheric moisture and clouds, influencing how much sunlight is absorbed and how aerosols form, processes that, in turn, affect cloud formation and local climate patterns. Clouds also touch human psychology in subtle ways. Their presence shapes how much natural light reaches our eyes, affecting circadian rhythms, melatonin production, and stress hormones. Depending on their color, form, and motion, clouds can calm us, inspire melancholy, or fill the air with tension before a storm. Clouds are far more than beautiful shapes drifting across the sky. They are living, dynamic systems that regulate climate, control the flow of water, sustain ecosystems, and even influence human biology and emotion. Each cloud is a microscopic laboratory where water, air, and tiny particles interact in countless ways, and the results of those invisible processes can be felt across the entire planet, from rainfall and temperature to our very mood and daily life. The same clouds that bring life can also become powerful threats. The most obvious example is flooding, the result of excessive rainfall. When cumulonimbus or nimbostratus clouds gather immense volumes of water and remain over an area for hours or days, the ground simply cannot absorb it. Rivers overflow, city streets turn into waterways, and mountain slopes collapse into landslides. History has shown that such floods can affect hundreds of thousands of people and entire ecosystems at once. Tropical storms and hurricanes are another expression of cloud-driven destruction. These massive systems of towering cumulonimbus clouds, powered by warm ocean waters, can produce winds exceeding hundreds of miles per hour, torrential rains and storm surges that devastate coastlines, crops, and infrastructure. Tornadoes, though smaller, concentrate even more energy, a swirling column of air capable of uprooting trees, tearing apart homes, and reshaping the landscape in minutes. In all these cases, clouds act as catalysts for atmospheric forces, storing moisture and energy until they're released in explosive, destructive bursts. Hailstorms are another danger, born inside thunderclouds. When ice crystals are lifted again and again by strong updrafts, they grow larger until gravity wins, sending down hard spheres of ice that damage cars, roofs, crops, and livestock. In some parts of the world, hail is even more common than heavy rain, and often far more destructive. Lightning presents yet another peril. A single bolt can ignite fires, cause electrical failures, or strike a person with a force beyond human endurance. Within cumulonimbus clouds, water droplets and ice particles collide, separating positive and negative charges. When the imbalance grows too great, the sky discharges in a blinding flash, lightning racing toward Earth at incredible speed. Remarkably, some clouds can cause damage far from where they appear. Supercell storms, for instance, can generate intense winds and heavy rain tens of miles away from their core. This shows how vast and interconnected the atmosphere truly is, how a single storm system can shape weather and lives across entire regions. And yet, humans also influence clouds. Industrial pollution, vehicle exhaust, and energy emissions release vast amounts of particles and chemicals into the atmosphere, materials that serve as condensation nuclei. In many regions, this means clouds form more easily, become denser, or take on different properties. The result is a double-edged effect. More clouds reflecting sunlight and cooling the surface in some places, but disrupted rainfall and droughts in others. Human influence doesn't stop there. Weather modification techniques, such as cloud seeding with silver iodide, aim to induce rainfall in dry regions. Though used on a limited scale, these experiments show that humanity can alter the local water cycle. But such interventions are unpredictable. Changing the condensation process in one cloud can affect nearby weather systems in ways we don't fully understand. Cities, too, reshape clouds and weather. The heat released by buildings, factories, and traffic creates so-called urban heat islands, which lift air and modify convection currents. That's why rainfall is often heavier near cities than in rural areas. Air pollution adds soot and dust that darken clouds, changing how sunlight reaches the ground and subtly shifting the local climate. In short, humanity's impact on clouds is vast and multi-layered, from chemical and physical changes in the atmosphere to local weather shifts and even global hydrological cycles. Every single human action, multiplied millions of times, alters how clouds form, how often it rains, and how energy moves through the sky. Clouds, once purely natural creations, have become silent witnesses to our presence and our influence on the planet itself. A cloudless sky, so-called clear sky, might look simple, but it's actually the result of a delicate atmospheric balance. Clouds form when water vapor condenses around microscopic particles called condensation nuclei. Things like dust, pollen, sea salt, or pollution. When the air is too dry or lacks these tiny particles, condensation doesn't occur, and no clouds appear. Clear skies often occur under high atmospheric pressure, when air sinks from higher altitudes toward the Earth's surface. Rising air cools and forms clouds, but descending air warms up, lowering its relative humidity and keeping water vapor invisible. These high-pressure systems, known as anticyclones, bring calm, sunny weather and perfectly clear skies. Temperature and humidity layers also play a role. Even if the air near the ground feels moist, a dry layer higher up can eat away at rising air masses, stopping clouds from forming. That's why we sometimes see an intensely blue, cloudless sky despite the humidity we feel at ground level. In deserts, clear skies are even more common. The air there is naturally dry, and the atmosphere contains few particles to act as condensation centers. That's why the Sahara or the American Southwest often offer endless days of pure, brilliant blue skies. Yet even this simplicity is fleeting. The smallest change in temperature, the arrival of moist air, or a gust of dusty wind can trigger cloud formation within hours. In reality, a cloudless sky isn't a static state. It's a momentary equilibrium in a restless atmosphere, a snapshot of invisible physical and chemical forces constantly at work above us. Clouds, though often seen as mere scenery or weather, have long fascinated scientists, engineers, and meteorologists, striving to understand and predict the forces shaping our world. As early as the 19th century, meteorologists noticed that specific cloud types appear under predictable weather conditions, allowing them to forecast rain, storms, and temperature changes. Today, that knowledge has evolved dramatically thanks to satellites, radar systems, and computer models that can observe clouds from space and analyze billions of atmospheric data points in real time. Clouds play a crucial role in climate models. Their presence affects how sunlight is reflected, how the Earth's surface is cooled or warmed, and how moisture and energy are transported through the atmosphere. That's why scientists use advanced computer simulations to predict how climate change, Increasing greenhouse gas emissions or air pollution will influence the future types and distribution of clouds. Even a small change in how clouds form, their density or height, can have enormous consequences for local rainfall, hurricanes, or droughts. Technology also allows us to quite literally listen to clouds. Weather radars and lidars measure droplet size, the vertical speed of air currents, chemical composition, and the internal structure of clouds, enabling precise forecasts of rainfall, storm warnings, and the monitoring of extreme weather phenomena. Drones and weather balloons equipped with cameras and sensors rise into clouds, delivering data on pressure, humidity, temperature, and aerosol content, information that was once impossible to obtain. Some technological experiments even make it possible to modify clouds within a limited range. The so-called cloud seeding, introducing silver iodide or other particles into the atmosphere, can increase rainfall in dry regions or reduce the intensity of hailstorms. Although it remains a controversial and unpredictable technology, it shows that humans are beginning not only to understand, but, at times, to influence atmospheric mechanisms. Meteorological satellites allow for the observation of clouds on a global scale. Thanks to them, we can track hurricane cycles, the movement of atmospheric fronts, and changes in cloud distribution caused by global warming. These data are vital not only for weather forecasting, but also for climate researchers, oceanographers, and biologists studying how rainfall affects ecosystems. Clouds also have less obvious technological uses, in optics and communication, for example. Phenomena related to clouds, such as light scattering, allow scientists to study the atmosphere and solar radiation, essential for renewable energy research. The study of clouds also contributes to a better understanding of extreme weather events, helping engineers design infrastructure resilient to floods, hurricanes, and storms. Clouds have become more than just decorations in the sky. Thanks to technology and science, we can now observe them with unprecedented precision, analyze their influence on climate, predict extreme phenomena, and in a limited way, even interact with them. They are both a challenge and an inspiration to scientists, revealing how complex and full of energy the atmospheric processes above us are. Often unnoticed, yet vital to life on Earth. In space, too, we can speak of clouds, though they differ completely from those on Earth. On other planets and in interstellar space, clouds are made of different substances and shaped by entirely different physical conditions, yet they play an equally fascinating role in forming the environments we study. On planets like Jupiter and Saturn, clouds form massive layers of gases, mainly ammonia, methane, water, and other compounds, floating within intensely dynamic atmospheres. These clouds not only give the planets their distinctive striped and swirling appearances, but also transport heat and energy through their atmospheres, generating extreme phenomena, giant storms, including the famous Great Red Spot on Jupiter, which is larger than Earth and has persisted for centuries. On Venus, clouds consist mainly of sulfuric acid, creating a dense, toxic veil around the planet. They are extraordinarily thick, reflecting more than 70% of sunlight, and concealing the planet's surface from view in visible light. These clouds are also responsible for Venus's extreme greenhouse effect, which raises surface temperatures above 490°C, showing how profoundly clouds can influence a planet's climate. Mars, though known as the Red Planet, also has clouds, thin, icy formations made of water ice crystals or frozen carbon dioxide, dry ice. They form mostly in the higher layers of the atmosphere and are more delicate than Earth's clouds, yet they still play a role in the local weather cycle, influencing heat and moisture transport. In interstellar space, we use the term clouds in a completely different sense. Nebulae. These are vast clouds of dust and gas from which stars and planetary systems are born. Nebulae, such as the Orion Nebula, can span thousands of light years, composed mainly of hydrogen, helium, and heavier elements, and their condensation leads to the birth of new stars. This shows that clouds in space are not only beautiful, but fundamental to the formation of life and matter in galaxies. It is also fascinating that on some moons, such as Titan, Saturn's largest moon. Clouds form from methane and ethane, which, under low temperatures, condense into droplets, creating rains of liquid hydrocarbons. It's a hydrological cycle entirely alien to Earth's, yet it operates in a similar way. Evaporation, condensation, precipitation, all happening under extremely cold conditions. In space, clouds show that processes of condensation, gas movement, and structure formation are not unique to Earth. Depending on atmospheric chemistry, temperature, and pressure, they can take icy, acidic, or hydrocarbon forms, or, in the case of nebulae, become truly cosmic, composed of elements that give birth to new planetary systems. Each cosmic cloud is a fascinating laboratory of physics, chemistry, and dynamics, teaching us how universal yet endlessly diverse the processes of gas formation and motion are throughout the universe. When we look up at the sky, we see clouds drifting above our heads, changing shapes, colors, and moods. They are part of the natural cycle of water and energy in the atmosphere, evaporating, condensing, and falling back to Earth as rain. But sometimes, over cities, something appears that looks like fog, resembles a cloud, yet is something entirely different. Smog. It could be called a human cloud, because unlike natural clouds that give life, smog carries toxins, disease, and destruction. It is a mixture of dust, soot, nitrogen oxides, sulfur oxides, and other gases that hang in the air, forming a dense, almost suffocating veil over urban landscapes. Smog is produced by the burning of fossil fuels, coal, oil, gas, as well as wood and biomass. In cities, emissions from vehicles and industry combine with natural dust, soot, and aerosols suspended in the air. Under certain meteorological conditions, such as lack of wind, high humidity, and temperature inversions, all these components become trapped near the surface, forming a long-lasting toxic fog. The effect is particularly visible in winter, when heating systems work at full capacity and air in valleys and cities becomes stagnant. Smog affects people in dramatic ways. Fine particulate matter, PM2.5 and PM10, is so small that it penetrates deep into the lungs and from there enters the bloodstream. It can cause chronic respiratory and cardiovascular diseases and even alter brain function. Gaseous pollutants such as sulfur dioxide, nitrogen oxides, and ozone further irritate mucous membranes, increase infection risk, exacerbate allergies, and can trigger inflammatory responses throughout the body. Studies show that in the most polluted cities in the world, smog can shorten life expectancy by several years, and during episodes of extreme pollution, death rates can rise dramatically. Smog also impacts the environment. Acid rain, formed when sulfur and nitrogen oxides react with rainwater, acidifies soil, destroys vegetation, and degrades lakes. Dust settling on leaves limits photosynthesis, affecting plant growth. Pollutants enter rivers and seas, disrupting aquatic ecosystems and causing mass die-offs of organisms. Even urban animals, birds, and insects suffer from toxic air. Their immunity weakens, and reproduction becomes more difficult. The relationship between smog and natural clouds is fascinating. Smog doesn't just float in the air. It interacts with real clouds, altering their composition, structure, and precipitation patterns. In some cases, smog particles act as condensation nuclei around which water droplets form. In others, they inhibit normal rain formation processes, leading to droughts in regions far from the source of pollution. Smog is therefore not only a local issue, but part of a complex atmospheric dynamic. Smog also influences the global climate. Soot particles absorb solar radiation, heating the air, altering local convection currents, and affecting surface temperatures in regions hundreds of miles away. Historical observations show that massive volcanic emissions combined with human pollution have, at times, temporarily lowered global temperatures. This demonstrates that even seemingly tiny particles suspended in the air matter, not only for human health, but for the entire climate system of Earth. Modern technology allows us to track and even attempt to control smog. Networks of air quality sensors in cities, Earth monitoring satellites, and air pollution forecasts all help warn residents, plan traffic, and reduce emissions. Some cities impose bans on combustion engine vehicles on days of extreme pollution or regulate heating systems to cut particulate emissions. This shows that, although smog is a serious problem, tools exist to help mitigate it. When we look at the thick gray fog hanging over a city, we see not just a visible layer of air, we see a complex chemical, physical, and biological system that affects the lives of millions, shapes ecosystems, and influences the climate. Smog teaches us that the atmosphere is a delicate, dynamic system, vulnerable to human activity, and that every human interaction with air leaves a lasting trace above our cities. It is the human cloud, a reminder that our civilization and nature are constantly intertwined, and that observing and understanding these processes is crucial for the future of life on Earth.